Hello and welcome to our presentation titled Design Optimization and Uncertainty Analysis of Deployable Viscoelastic Tape Springs. My name is Wolfgang Klimm and I'm the presenting author. However, this work was done in collaboration with Veli, Bugra, Ozdemir in the Structures and Materials Design Laboratory of Dr. Kawai Kwok at the University of Central Florida. Before I begin, I would like to give you a quick outline of this presentation. I'll start with a brief introduction to deployable structures and the typical challenges they face. This will also include a quick review of the structural simulation of viscoelastic components. Then we will jump into the machine learning portion and I will tell you more about the design of experiment and the Gaussian process regression we utilized to study the recovery behavior of a viscoelastic tape spring. Next, we will touch the topic of multi-objective optimization, considering the output from the surrogate model as an objective and impose two more objectives for which a Pareto front was sampled. And finally, we will touch the field of uncertainty analysis, looking into the robustness of our ideal design points via Monte Carlo simulation. A comparison of a local and global sensitivity analysis will conclude the paper. Let me start with an introduction into deployable structures. Folding and deploying of space structures makes missions either more economic by using up less space within the launcher fairing or are even critical to enable a mission altogether. Deployable structures, however, face challenging and contradicting requirements such as high accuracy in the deployed state but low strains in the folded configuration. Also, the repeatability of folding and deployment must be possible to allow for a test sequence before launch. And finally, very high reliabilities are necessary since deployment is very often mission critical. Common examples of folded structures are reflector antennas, solar sails, drag sails, and star shades due to their typical sizes of several square meters. We would like to focus on tape springs as one of the most fundamental deployable component though. The photograph in the lower right hand shows a tape spring hinge made from two tape springs connected with end fittings. The photograph on the upper right hand shows the folded configuration of this hinge. Early tape springs were manufactured from stainless steel or copper beryllium, whereas the focus of ongoing research lies on tape springs manufactured from carbon fiber reinforced polymers. These materials often offer a very high specific stiffness and allow tailoring the mechanical properties by layout variations. However, the polymer matrix introduces a time-dependent behavior of the mechanical properties, which is known as viscoelasticity. Viscoelastic materials exhibit a material behavior which is a combination of elastic and viscous characteristics. Applying, for example, a constant strain quickly will yield an elastic response. However, when this strain is kept constant, a decrease in stress over time can be observed subsequently. This effect is known as stress relaxation. The time-dependent behavior of viscoelastic materials can be modeled with a Prony series of the form we see in the center of this slide. E infinity here represents the infinite Young's modulus, whereas EI and rho I are the Prony coefficients and relaxation times respectively. With this equation, the relaxation modulus can be calculated at any given point in time t. This is particularly useful when the stress relaxation in a folded deployable structure is analyzed, since this decrease in stored strain energy can be estimated. For this project, we chose the available Prony series for PMTF4, a space-graded epoxy matrix. The relaxation modulus of PMTF4 is illustrated in the figure on the right-hand side. Here we can see that the modulus decreases from approximately 5,000 megapascal to about 4,000 megapascal within 10 to the power of 6 seconds, which equals about 12 days. From the brief introduction on the previous slide, several challenges can be derived when we deal with viscoelastic tape springs. First of all, stowed high-accuracy space structures are most sensitive to viscoelastic effects due to their prolonged stowage times and possibly elevated temperatures before launch. In addition, the tightest packaging often comes with high strains in the folded configuration. These three effects contribute considerably to high stress relaxation and a reduction in stored strain energy. If the deployment mechanism relies entirely on the stored strain energy, the stowing conditions can become so detrimental that successful deployment is prohibited altogether, an effect which has been demonstrated analytically, experimentally, and by structural simulation by several research groups. Consequently, this project is focused on studying the influence of three geometrical parameters on the recovery behavior of a folded viscoelastic tape spring via machine learning in an attempt to determine the optimal design under uncertainty aspects. At this point, it should be pointed out that Yang et al. Have already successfully applied the surface response method to folded tape springs in order to predict the maximum stress, the steady moment, and the peak moment from surrogate models. In order to generate the necessary training data for the recovery behavior of viscoelastic tape springs, a finite element model was developed. In the structural simulation, the tape spring is cantilevered as illustrated in the upper right hand, and goes through a cycle of static folding, a stowage step including stress relaxation, a dynamic deployment step over 5 seconds, and finally a recovery step during which the tape spring attempts to minimize the remaining strain energy and approaches its initial shape. The folded shape of the tape spring is illustrated in the center of this slide. In this scenario, the three design variables are the transverse radius r, the thickness of the cross-section t, and the subtended angle theta. They are further illustrated in the figure on the right-hand side. The two quantities extracted from the structural simulations are the tip deformation after 23 days of recovery and the first two eigenfrequencies. The eigenfrequencies, however, proved to be well above 15 Hz for all design points and were dropped at this point, since typical requirements for the eigenfrequencies of space structures are above 1 Hz. For further details on this modeling approach, I would like to refer you to our paper or the references provided here and in the paper. The design of experiment is the first necessary step before any machine learning approach can be applied. We chose to sample our 3D design space with the Sobel sequence since it allowed us to add more points along the way compared to Latin hypercube sampling, which would have required a firm number of design points from the beginning. We chose a large number of 250 design points and evaluated the residual deformation of the tape spring tip. The sampled design space with the corresponding residual deformation represented by color can be seen on the right-hand side. Each simulation took between 20 minutes and 2 hours and were run on several nodes of a cluster with 16 Intel Xeon 64-bit CPUs each. The design space of the radius was limited to the interval between 15 to 25 mm, the thickness to 0.1 to 0.3 mm, and the subtended angle to 60 to 120 degrees. Next, we applied Gaussian process regression on the residual deformations extracted from the structural simulation executed at the training points. This was done in the machine learning toolbox by MATLAB. A hyperparameter optimization was carried out to minimize the root mean square error of the resulting surrogate model. The hyperparameter optimization could choose from 4 basis functions, namely a zero, constant, linear, and quadratic basis function. The available covariance matrices to choose from were the rational quadratic, the squared exponential, Maton 3-2 and 5-2, as well as the exponential covariance matrix. The resulting surrogate model with a minimal root mean square error of 0.007734 mm was built by a zero basis function with an isotropic squared exponential covariance matrix. The figure on the right-hand side illustrates the prediction performance of the surrogate model at the design points. The leave one out approach was chosen here, meaning the design point for which the residual deformation was predicted was not included in the training set of the surrogate model. The prediction accuracy is very good, especially for lower residual deformations. Due to the initial uncertainty when choosing the size of the training set, an investigation of the influence of the number of training points on the root mean square error of the surrogate model was carried out. The graph on the right-hand side shows the decrease of the root mean square error with an increase of number of training points. The training points here were chosen in the order of the Sobel sequence generation. Whether the value of the root mean square error is acceptable or not depends on the deformations, which will be predicted with the surrogate model. For the very small deformations in the following slides, at least 150 training points should be chosen to train the surrogate model, though no major improvement can be seen beyond 200 training points. These numbers justify the large training set chosen initially. The press RMS error equals 0.00756 mm, which is acceptable for the predictions of deformations between 0.01 and 0.1 mm in the following sections. Next, the residual deformation predicted by the surrogate model was combined with 2 more objectives, namely the volume and strain when the tape spring is flattened and wrapped on a drum. The latter is a common approach to store deployable booms. We limited ourselves to 3 objectives in order to easily visualize the forming Pareto front. More objectives, such as the strain energy in the folded configuration or the previously mentioned eigenfrequency, are also possible though. In order to sample the Pareto front, a controlled elitist non-dominated sorting genetic algorithm with an initial population size of 1000 was applied. The initial population was random but of a uniform distribution. 50 elite points were chosen to speed up the convergence of the Pareto front. The best 700 points were extracted from the Pareto front and 3 constraints applied in order to reduce the set of the ideal design points to a manageable size. A residual deformation of less than 0.06 mm, a volume of less than 600 mm3, and a strain of less than 0.5% were required from the design points. This reduced the Pareto set from 700 to 42 points, for which the following uncertainty analysis was conducted. The 3D Pareto front is illustrated in the upper right corner, whereas a 2D view is given in the lower right corner, focusing on volume and residual deformation. In these two plots, the black dots form the 700 Pareto points, whereas the red points represent the chosen 42 design points after the constraints were applied. For each of the 42 remaining design points, normal distributions were applied to their 3 input parameters, with the mean of the chosen design point and a fixed standard deviation of 1 mm, 1 degree, and 0.01 mm respectively. Then each design point was sampled 100,000 times, drawing slightly varying design sets from the corresponding normal distribution. The variation of the residual deformation for one design point was plotted in a histogram and can be seen in the upper right figure, represented by the gray area. After obtaining the variation, several attempts were made to fit a distribution to the output histogram. Fitting a distribution helps to predict values at locations where output points are scarce, such as long-tail regions of the histogram. The Burr distribution was capable to capture the output histogram best, compared to a normal or log-normal distribution. It should be pointed out that choosing a normal distribution would lead to tighter confidence intervals and therefore has to be considered less conservative. Based on the fitted Burr distribution, the 95% confidence intervals were determined for each of the 49 remaining design points. The figure in the upper right provides the mean values as well as the confidence interval in a graphic manner. Exemplary for one design point, the figure in the lower right provides the cumulative distribution function. These graphs illustrate the previously mentioned tighter confidence intervals a normal distribution would yield compared to the Burr distribution. The table on the lower left provides the 5 best design points in terms of mean value and upper confidence interval. It should be highlighted that all of these design points have a thickness close to the minimal allowed value of 0.1 mm. Also, the radius and the subtended angle differ only slightly. In addition, it's worth noting that the lowest mean value also has the lowest upper confidence boundary, a fact that is not always guaranteed. A local sensitivity analysis was conducted on the ideal design point originating from the previous multi-objective optimization and the subsequent uncertainty analysis. Again, the input parameters were varied slightly and the resulting residual deformation was predicted with the surrogate model. The influence was then graphically analyzed in the 3 plots shown here. It can be seen both in the left and in the right plot that the thickness plays a minor role in affecting the residual deformation, since the isolines in those plots run almost vertically and horizontally respectively. The plot in the center though shows an almost equal influence of subtended angle and radius on the residual deformation, indicated by isolines under 45-degree angles. Since this local sensitivity approach varies with the interval size chosen, a global sensitivity analysis was done on top. In comparison, a global sensitivity analysis was conducted over the entire design space. The elementary effect test was utilized via the SAFE toolbox for MATLAB. The results of the global sensitivity analysis are shown in the 2 graphs on the right-hand side. The analysis revealed the subtended angle to be the most influential parameter on the residual deformation over the entire design space. The results indicated radius and thickness of the cross-section to be of equal rank. The sensitivity analysis was also extended to the 700 points of the Pareto front and the most influential parameter determined for every design point. The results are indicated in the lower left corner. It can be seen that almost all design points from the Pareto front are most sensitive to the changes in the subtended angle, whereas a few outliers are most sensitive to the changes in the radius. This supports the results we've seen from the global and local sensitivity analysis previously. And this brings me to our conclusion. First, I would like to state that a surrogate model from the Gaussian process regression can capture the recovery behavior of a viscoelastic tape spring very well, The required number of training points should be further investigated, though, and possibly reduced. Also, stowage and recovery times would be interesting input parameters to add. Next, the chosen non-sorting genetic algorithm seems overpowered for the stated multi-objective optimization. However, it offers the capability to add several more objectives, such as the mentioned strain energy in the fault configuration and the eigenfrequencies. The Monte Carlo simulations gave valuable insight into the robustness of the chosen design points. The derived 95% confidence intervals offer a new approach to the prediction of deployment success. The global and local sensitivity analysis revealed the influence on the residual deformation and ranked the input parameters accordingly, giving valuable insight into which parameters should be controlled most carefully during manufacturing. And finally, future work will focus on extending the current model to carbon fiber composite material model, as well as verifying the surrogate model with experimental data. And finally, we would like to thank Dr. Viana from the University of Central Florida for his helpful discussions and guidance on Gaussian process regression and uncertainty quantification. And with this slide, I'd like to finalize the presentation, design optimization and uncertainty analysis of deployable viscoelastic tape springs. I would like to thank you for your attention, and I'm looking forward to hearing your questions during our designated question and answer session on the afternoon of June 15.